Yes, we can now start. This is our last lecture, and hopefully, after this one, you will be like experts in connected vehicle networks. Okay? Because the goal here, as you have seen, was for you to learn about this type of networks. Okay? Then, okay, all these very interesting concepts such as computing paradigms, cybersecurity, and today about artificial intelligence, because the idea is for you to be able, or at least for us to be able to use all of these concepts in connected vehicle networks. Okay? As I've mentioned, today we're going to talk about artificial intelligence, and of course, because this is our last lecture, I will also go over future research directions, because it is actually not only about what it's available, but also on what can be done more, or what are the next steps. Let me just confirm one little thing here. Okay, continuing. I will actually start by just quoting this very, it's actually a very interesting a paragraph or an opinion of these two researchers, in this case, Russell and Norvig, because of course that some say that there are a lot of theories that the world has a lot of years, okay? And when you start thinking of all from that small cell until these complex systems that we have, in this case, our cells are actually quite quite complex system, we arrive into the conclusion then that it is actually remarkable how we, in this case, a sack of meat, as some could say, okay, a bag of meat, can actually perceive, understand, predict, manipulate, okay? Because what we try to do, we try to understand a lot of things. Some, of course, that we have been acquiring a lot of knowledge until today, okay? There are a lot of scientific discoveries that have been made, but, as you can imagine, there is a lot of things that we still don't know, okay? For instance, black holes, okay? Even here in computer science, okay, there are a lot of things. That's why artificial intelligence, it's actually very important. But when you're talking about artificial intelligence, if you think that, okay, even we started our evolution, played a significant role in what and how we are today, okay, we are trying actually to do the same, okay, but of course, when I say to do the same, there is also this, if machines start thinking as us, start gaining intelligence, then maybe one day we will disappear, right? That's actually evolution. The weak over time actually disappear, but nonetheless, it is always good for us to find ways, of course, of understand, because by doing so, we are also understand how our brain, our systems actually work. Therefore, the role of machine learning. But when we are talking about this specific topic, our goal, we will mainly focus on two areas of artificial intelligence. In this case, machine learning, okay? You are experts, right, in machine learning, aren't you? That's good. And I'm not quite sure if you are aware of the artificial immune systems. Are you aware of those? No? Okay. You will learn something today then. Okay. When we are talking about the artificial immune system, okay, we first need to understand, or at least you need to understand, because this concept actually was borrowed from biology, okay? We human being creatures, we have some sort of an immune system, but in this case, it's the biological immune system, that is what allows us to continue living. Because if you don't know, the world it's actually quite aggressive. Okay, it's really, really, really aggressive. There are a lot of stuff out there. Okay, and we continue breathing because our immune system actually it's able to adapt, to learn. Okay, it has been learning over time. I'm not sure if you're aware, but every winter, do you know that it's like the flu virus? There is every winter there is actually a new or some sort of a new and mutated virus, right? You're aware of that, right?
Yeah.
Okay. And by getting infected, that's actually, unfortunately, that's the only way. By getting infected, you are actually improving yourself. You are learning, your system will learn, and next time you get infected with the same thing, what will happen? You're immune. Okay? Then, if you already know that there is a system that is actually this smart, why not to use it in computer science? Okay? That's why you have the artificial, because what we are doing here, we are basically using this computational intelligent technique, okay, in order to, we are applying these concepts in other areas. But okay, let us see. How does our biological immune system works? The concept is simple. You have something that is called self, okay? By self, it's that it belongs to your body, okay? And you have other things that are pathogens, okay? That are basically what's considered non-self, okay? According to some theories, the goal there is once or if you get something non-self in your bodies, then what will happen is that your antibodies will go there and kick that thing off. Basically, when you get infected, what is happening there is that it's like a dance. Your system is fighting. That's why you get fever. It's basically your system reacting and trying to eliminate the disease. Okay? But there is also another theory. It's actually called danger theory. That says that, we actually are not, or our immune systems is not actually going against something foreign. The theory, they say that it's actually when this theory basically says that the immune system reacts to danger. Okay, there is actually, according to them, the normal death of a cell. Okay, but if for some reason some cell is having some sort of an abnormal death, then some sort of a danger signal is actually emitted, sent, and all those antibodies that are in the vicinity of this danger region, okay, are actually activated in order to fight or to go and check what is actually happening. Okay, then you have actually a danger signal that has some sort of a radio, and every cell that is in the vicinity goes there and tries to actually react to that specific incident. That's what danger theory says. Any questions? Okay. Then we have the other thing that you are experts. It's machine learning. And basically I will be fast because you are experts on this. Because here we are trying to identify patterns, and in some cases we are able to forecast based on human data. Okay, and we have here these two main fields. Okay, these are the supervised and unsupervised learning in this case that are based on focused on exact predictions, or even if you want in this case to cluster, basically creating description of data, in this case applying some sort of a clustering or dimensionality reduction techniques and things like that. Okay. Then, because we are talking about connected vehicle networks, it would be interesting for you to at least to be aware of some solutions that use these techniques. In this case, we are talking about this research paper that is the RefIUV, okay? Because it's quite common. One of the things that's more common that you see on the internet, and that's actually not only related with the internet. Reputation. You are aware of reputation, right? That's actually a mechanism that we all use in our daily lives. How do you build your friendships? Sometimes you, or over time, if this person that you are interacting somehow you see that the outcome of this interaction over a considerable period of time is actually valuable, then you start developing some sort of a friendship with this person. But there is another concept, okay? It's trust, okay? It is actually different from reputation. What is trust? I will give you an example. Your mother. What do you think? When you're, for instance, analyzing the trust concept, that's something innate. When you're talking about your mother, it's not an idea of reputation, or I'm developing this thing with my mother based on what she's doing. No. It's like you were born, and even without seeing her, but you somehow develop a connection. Okay? This is somehow the trust that you have with your mother, or even you could say your father also, but that's also debatable. Okay, let us not go much into that. Okay, continue. Then reputation. If you go online shopping, what happens? The first thing that you see, ratings, right? Why? Because you want to see beforehand if, okay, you will be wasting money, or at least you will make good use of your money. Okay, therefore, reputation. When you're talking about, even for instance, connected vehicle networks, because the goal here is for nodes to be exchanging information over the network. And you know that some nodes may actually don't follow the protocol. By not following the protocol, I mean they may not send forward message of other nodes, because imagine, for instance, that you want to send data from here to Brighton, okay? You already know that you have like all these buses that go from here into there, okay? One of the things that you could do is, okay, let me use mobile networks, then you will send all that data from here into there, or you could just use, for instance, buses. Your data is sent to some storage on the bus, and the bus then, since he's going there, he will take your data and then he will basically send into the other thing. But the goal usually is that if you want, you need to decide which bus or which bus company you will select to carry your data. Okay? Why? And this can be used based on what? Based on reputation. Okay? Then what we are trying to do here is basically to, based on the outcome of these interactions with other nodes, decide if these nodes are actually good or bad. Okay? When you're talking about the RefIUV paper, what they have proposed in this case, they use this the beta distribution function. Okay, and when we're talking about that, we have this, that it's the alpha and the beta, and when we observe a good behavior, we increase alpha. And when it's a bad behavior, we basically increase beta. Okay? Simple. If you have that alpha and beta are both 1, what happens in that case, it's basically, we are basically telling that we don't have information about the behavior of this node. Because if you calculate the beta distribution or the value associated with alpha and beta equals to 1, then you will get 0.5. That's actually the absence of knowledge. If, for instance, you start increasing, if this node start behaving accordingly, then you start increasing beta, and therefore you will see that it will tend more into one of the sides, saying that this guy is behaving accordingly. Okay, this is actually how this works. But in this case, we use this Bayesian learning approach in order to, because this is based on the information, or at least when you're saying first-hand information is based on my direct interactions with other nodes, okay? But in order for these systems to converge much faster, what they actually need to do, they also need to receive opinions, in this case, second-hand information from all other nodes of the network. It's similar to say, okay, okay, this is an example, okay? She, okay, is a node, okay? What will happen if she, by talking to you all, she's learning, and she will start having a feeling of how you are behaving, okay? But in order, because that is actually direct information, she could also do another thing. She could say, okay, I want to interact with that other guy, but I don't know nothing about that guy. What will I do? In that case, she will take into account what others are saying about that person. Okay? But there is a problem here, as you can imagine. What is the problem? By just listening and considering others' opinions, what will happen? This is real life, huh? People are mean sometimes, you know.
You might be biased.
Okay, yes. And if you have more than one, what will happen?
You might misheard something.
Yeah. You start getting confused. Some guy says, oh, that guy is a good man. Oh, that guy's a bad guy. Then what happens here is that this guy thought, okay, there may be a problem associated with the information that I'm receiving, and then what I will do, I will try to apply some sort of a similarity metric, taking into account the information that I'm receiving. What am I saying with that? I will have to analyze the opinion of all those guys, and I will have to average based on what everybody's saying. If most of the guys are saying that that guy is bad, then most probably that guy is bad. Okay? You understand? But of course, this is second-hand information, and usually opinions of others shouldn't have the same value or the same weight from this information that is actually collected directly, right? But the other thing that actually was proposed here was the use of this bio-inspired algorithm. Because if I want, for instance, to identify if that guy is actually not behaving well, and I have this hinge, okay, I know that, okay, most probably that guy is not behaving well. What you will do, you want to be sure. Why? Right? Isn't that right? How can you do that? You could, therefore, test that person. Okay? How are you going to test here? You know that our goal here is to send data, right? I know that most probably if I try to send him data and he's able to relay data to someone that I trust, then what can I say? Okay, that guy may be good. Okay? Therefore, this thing here is actually what is happening, because if you remember, it's like it was established a dangerous signal based on a given node, And then what the goal was to inform all those other white cells on the vicinity, right, in order to act. Therefore, this approach is trying to do something similar to that, but in this case, it's trying to identify if really that guy is, in fact, a misbehaving node. This approach is actually fully distributed. Why? Because here, each node, okay, needs to arrive into a conclusion of if the other nodes are actually misbehaving or not, okay? It's not like sending all this information so that a central entity can actually have a global view and arrive into a conclusion. Okay, this is a block diagram. What happens here is that you have this mechanism that's called a watchdog. Okay, it's actually collecting information, and then based on this information that we are collecting, and as you already know that we are applying a beta distribution function, we have alpha and beta, and we increase alpha for good behavior and we increase beta for bad behavior, and then we send this first-hand information to the reputation module. And as you can see here, we also have that bio-inspired mechanism, but also what we can do, we can incorporate second-hand information, and based on the K-means algorithm, and we are able to apply similarity to the information that we are receiving, and then we also input this so that we can then send all this information to the decision module. And what will the decision module do? Classification. Basically say good or bad, in this case forward message, or simply do not cooperate with that other node. Questions? No? Yes? Let us continue. Then we have here another very interesting concept, okay? You are already aware of edge computing, right? You are already aware of edge computing. We have spoken of vehicular fog computing, vehicular edge computing, and vehicular cloud computing, okay? What happens here is that when we are talking about, or at least the motivation underneath edge learning, is that we have, in order for us to reduce delay associated of sending all this raw data to the cloud, we could perform part of this computation or even storage at the edge of the network. And you already know that machine learning is actually a very good tool, right? A very good techniques. Then by combining both of these, okay, knowing that in connected vehicle networks will actually end up generating a lot of data, then you are able to process this information where? At the edge of the network, instead of sending all this data to the cloud. Okay? It's like a win-win, as you can imagine, but not everything can be processed at the edge, okay? And sometimes you can do some sort of a pre-processing at the edge and then send the other data into the cloud. Okay, let us continue. Then we have this interesting image, okay, and as you can see here, because when we're talking about, for instance, we could consider this as some sort of a three-layer architecture where you have your devices, you have then edge learning, and you have cloud learning, right? What is happening here? First, here you are basically, and as you can see here, you have all this data that you are basically collecting from your devices. Then you are basically, this first step corresponds to downloading your model parameters, and then what you do, okay, you update basically your model based on this local data. That's what is happening here. You are updating your model based on local data, and then what you do, you basically send, or after you have done that, you're basically on step 2, you are basically uploading new parameters, okay? And then what you do, you are able to update your global model, because you can, and we will talk later on, okay? You can even consider this as a distributed system. You have many edge computing nodes spread throughout the network. You are able to collect all these nodes are actually have their own data, okay? But then you would also like to do what is called this sort of distributed computing, okay? But we will talk a little bit more about this. Then what happens here is that you may have a lot of edge learning applications, okay? But most of these applications are related with image processing, okay? For instance, security and surveillance, okay? What happens there is that you may have, for instance, for security, you may have images, and your goal is to identify, for instance, do image recognition, face recognition, okay? The other thing that you may have is, for instance, for surveillance, you may be monitoring fire, okay, in forests, okay? If you, for instance, you are trying to detect if you have smoke somewhere, what you can do, you can take all those images and send this for being processed somewhere else. You can do some other very interesting things, such as augmented reality, and this is even possible for you to do this in vehicles. If you're arriving in a given location, then you start receiving, for instance, all this information, all these personalized advertisements, okay, related to taking into account your own interests, okay. You can have also virtual reality and all those other, but one of the things that you need to consider here is that these are real-time applications, okay? And one of the requirements of real-time applications is that it's delayed, okay? You can't send this thing to the cloud because it will take a lot of time to go there and actually coming back. Then we start considering this case of distributed edge learning, because one thing is, okay, you only have your edge, you are considering only edge computing one unique site, okay, and if you consider, for instance, a mobile network operator, what happens is that they have many. They may have many sites, okay, many base stations with servers, in this case with edge servers, and this is actually also called mobile edge computing, okay? And then, even that they have all these sites, what they can do, they can actually then do this kind of distributed processing, in this case by gathering data, generating training data sets, pre-processing, and other interesting operations. By working collaboratively, they are able, in this case, to improve network performance. But there is here another issue, okay? There is, of course, how, okay, or even why we can obtain or achieve these kind of things. You have here two possible approaches, okay? One that actually consists in having some sort of a central entity, okay, where you're basically collecting all this information that is being basically being acquired over the network, and then what you do, you send this thing, okay, or part of this information to a given entity for further processing and decision making. Because at the end, what is happening here is that you are collecting data and then sending, after it being processed, sending so that someone can actually reach to a given decision based on the information that you are receiving. The other approach is actually more distributed, that is actually called based on some sort of an ad hoc network approach, because it actually implies what is called in-network processing, in the sense that each one of the nodes will actually do its own processing. Any questions? Interesting. Then we can see here some applications of distributed edge learning, for instance, and for this first one, because as you can see for this image, we have a lot of nodes. Okay, we have data, we have edge nodes, and of course we have here this node here that's actually some sort of an aggregator, a data aggregator. And the goal here, and it's actually one of the challenges when we're talking about a lot of data, a lot of devices generating a lot of data, is instead of sending raw data that each one of these devices is actually gathering, why not just pre-process that data before sending it for further processing on the cloud? What would be the advantage of that? You would be basically reducing the amount of data that, and therefore, because one of the big challenges that we are actually facing is that if you are sending too much data, then you are fully occupying those links. Okay, and considering that many other information should also be using them, it becomes a little bit unfair in that sense. Okay. In this case, what happened was that these actors or these authors, the idea here was to perform this kind of to determine the frequency of this global aggregation. Okay. And in this specific case, the big challenge, and taking into account the other challenge associated with machine learning, that is actually related with, if you have data, then one of the things that you need to do is actually to obtain a representation of this data, or at least a model that can be used for further processing, or in this case, okay? And in order for you to generate your model, what you will need to do, you need basically to train. And given or the amount of data that's actually being generated, in this case, because it's actually a considerable amount of data, then this may not be the most appropriate approach. Okay, therefore, in this specific case, okay, the idea here, or at least what these guys proposed, was to apply this gradient descent based distributed learning approach, okay, that has basically two steps. In the first step, what they do, it's basically a local update step, okay, and in this case, nodes are basically performing or adjusting their parameters locally, okay, because the goal most of the times is to minimize loss. And then there is the other global step, in this case, where information is sent to this guy here. We have another example of application of distributed edge learning in connected vehicle networks. And for this case, as you can see, we have here many interesting elements. Let us see. We have a cloud server, SDN controllers. Okay? Do you remember SDN, software defined networks? Do you know what those are? What are they? You're just shaking. Oh, yes, I know that thing. What are the software defined networks? Do you know? Do you remember? Oh, I remember vaguely. We'll talk a little bit about this later on, but you can consider SDNs as the concept that actually splits, because you have a network device, okay? Usually what happens is that you are trying to decouple what? Controlling functions from data functions. When I'm talking about data functions, are more related with how data is actually sent, okay, and you have control functions that basically selects or is the one who decides where this data need to be sent, okay. One thing is just sending data, selecting, for instance, I'm receiving this data in this port and I'm sending to the other port, okay. And the other thing is saying, okay, if you have many of those network devices, through which devices this data needs to be sent, okay? If I need to use switch 1, switch 3, switch 4, or any other devices taking into account the type of data and other configurations, okay? And in this case, what we have here, we have also roadside units, and as you can see, vehicles are able to interact among them and also to the roadside unit. What is our goal here? Intrusion detection, okay? What is intrusion detection? It's to be able to identify if something that's not supposed to be happening, it's actually happening in a network. For example, if there is some attacker, okay, that is trying to, because when you're considering vehicles, what will happen is that because they have actually communication capability, okay, what will happen is that others will try to take control of the vehicle to perform we don't know what, okay. Therefore, it would be desirable for us to identify if our networks or if attackers are trying to get into our network. For this specific system, okay, the authors actually considered, for instance, in their system model, because by system model they are considering all those elements that are associated with this, with their network. In this case, you have roadside units, you have SDN controllers, because it's based on the SDN controllers that you are able to decide to whom send information, and you have also a cloud server, okay? In this case, you have two steps, because that's usually what happens. First, you need to train, you need to create a model based on the information that you are observing from your network. And after you have this fantastic model, what you will do? You basically apply it, right, to detect your possible intrusions. But then I would also make you the following question. What is one of the main problems when we're talking about ML? ML applications. What is one of the big challenges that everybody faces?
Training.
Training, yes. More?
The data, how to collect the correct data.
Assume that you have already collected correct data. What is the challenge that you may face? You trained your data and then?
Deploy. Deploy in the business module.
Okay. And then?
Validating results.
Validation. Why is validation a problem? Because one thing is training and you think, okay, this is actually nice. But really, the false positive rates associated with ML unfortunately continue being high. Okay? That's why what happens is that everybody's fine-tuning, okay, this would work to my specific case, but if you then change a little bit, it doesn't work.
Overfitting problem?
Yes, that's another, overfitting, yes. Okay, any questions? Okay. Then let us talk about future directions. One of those, okay, because we are talking about connected vehicle networks, and I've already mentioned, okay, software-defined networkings. Why? Because as you can see how traditional networks are, you have like your network devices, you have, normally what happened was that you had data plane and the control plane on the same device, meaning that each device needed also to decide by talking with other switches what to do. But nowadays we are doing something different. We are having this programmable networks, in this case, where you have this controller that basically says, okay, this is what you need to do, okay? And then they, based on this information, the only thing that they are actually doing is just sending data, okay? Okay? Therefore, being considered as programmable switches. But the advantage of them being programmable switches is that they can do more than just forwarding data. Some other functionalities such as network functionality, such as for instance firewalls, you can even, depending on the programmable switch, you can also add that type of functionality by programming it. Okay? Quite interesting. Then we have, because what it's happening nowadays is that most mobile network operators are actually still implementing what? 5G, right? But what are we, academia and research, thinking of? 6G. If the industry is already fighting to profit from 5G, we are thinking of 6G. What will come, what follows in this case? I'm not sure if you remember, but one of the challenges of 5G was to obtain data rates from 100 to 1 gigabit per second, right? When we are talking about 6G, are you seeing this? You know what is this? When you're talking about speed, it's beta terabits. Yeah, bytes is for storage. And latency. Do you remember what was for 5G? Yeah, you're just like tossing a coin. That's the from 1 to 5, okay? And what we have here? But we have other interesting applications. For instance, localization. Do you know that it is challenging, even here in this room? How would you do to locate each one of you here in this room? It is possible. There are applications, because you'll say, oh, GPS doesn't work in those. Okay? There are other localization techniques that you can apply, but the challenge here is, of course, precision. But with 6G, the goal is to improve significantly precision. And even, for instance, for outdoor, what is the problem of outdoor? For instance, GPS. What is the precision? You don't have a clue. Yeah, usually precision. That's why usually when you are using your GPS, it is not showing 1 meter. It is showing like 10 meters. And then when you are close, you see 10 meters, then turn. That's precision. Okay? For you to have a precision of 1 meter, it's actually challenging. Okay? That's why with 6G, the aim is, of course, to get that. But the other problem, usually the other challenging problem, it's energy efficiency. Why? In 2013, okay, 4G, I think so, 4G was actually being deployed, still being deployed in many countries, okay? I bought a 4G capable phone. What was the problem? Sorry? No, how?
Now, saying maybe the technology you were ahead of the existing technology.
No, there was 4G back then. Yeah, there was 4G. I just bought a device to use 4G. But what was the problem?
It wasn't that spread out across the places.
What?
Like
There
4G.
was for, it wasn't the coverage. No, it's not. It wasn't the coverage problem. The problem, a hint. You can have a hint for the problem. Energy efficiency. Because back then, my battery with 4G could only last at most 24 hours. Okay? Do you know, for instance, for 1G or 2G, those dummy phones, how long do they last?
4 days.
A couple days, if not like a month. Okay? This guy is 4G ready, 5G ready. Okay? Even lasts more than that 4G device that I bought back then. Okay? It's for you to have an idea that energy efficiency is actually nice, because you may have a smartwatch, but if you have to charge every single night your smartwatch, it's a little bit annoying. Okay? Technology. We have also here serverless computing for the ones that are not aware. Okay? Quite interesting stuff. Okay, because you have cloud computing, then we are turning to serverless computing, and as you can see here, this is associated with the idea of basically allows applications, developers having immediate concerns of, and they don't getting concerns with the underlying infrastructure in this case. And we have the other thing here that's related with machine learning, because the good thing nowadays is that ML, and it's actually a trendy topic, because in most companies, it's not that like ML is like a new thing. It has been around for a lot of years, but lately, because of the amount of data, everybody wants what? Data scientists. Because they just realized that we have a lot of information, a lot of logs, and we can actually do something useful with that information. And you have here this interesting idea that shows the difference between traditional, where you have like your server, and usually when you have your server, you can have like a web server that's only doing that thing, nothing more than that. Okay, but when we're talking about serverless computing, as you can see, in this case, you can have many functions running on the same server without actually losing much performance. Okay, and this is it. Okay, you will also, I believe that you will have other very interesting topics in this, because here is for you to have this idea of all these very fantastic topics, and of course most probably help you in deciding, or I want to do something in that specific area. Okay? Okay then.